Hello everyone. Today we're going to look at transforming graphs and odd and even graphs. So let's start with transforming graphs. To translate a graph, you add or minus to the function or x. So starting with adding to the function overall, if you add 2 to fx, you basically move the function up by 2 units. And this is because of BODMAS. So fx is calculated first, let's say x squared, and then you get the answer, and then you plus 2. That means every value of y that is calculated from x, so 3 squared, 4 squared, 2 squared, 1 squared, they all get added by 2, meaning the whole graph is translated upwards by 2. Meanwhile, with translating left and right, you want to change the value of the x going into the equation. So if we minus 2, so x minus 2, and then put that into the function, what we're basically doing is changing the value of x in terms of like moving it to the right. For example, so a normal y equals x squared graph would go through the origin. However, if you use x minus 2, the 0 here would actually become minus 2, and minus 2 squared actually becomes 4. And so here, in this graph, if fx equals y equals x squared, 0 would actually correspond to 4. Meanwhile, 2 minus 2 is 0, and that's why 0 squared is 0, and that's where the x-intercept is. And this is quite counterintuitive. If you minus 2 to x, the graph actually moves right. And you have to keep this in mind when you're doing these things. It can get very confusing. All right, moving on to reflection. When you times the whole function by minus 1, you're basically reflecting it in the x-axis. And why this happens is because, let's say, again, y equals x squared. We have 2 over here. 2 squared equals 4. And then you times minus 1 to the whole function, meaning that every corresponding y value is flipped over here, and it turns into its negative value. And so that's why the graph is reflected on the x-axis. Meanwhile, if you times x by minus 1 before putting it into the function, you're reflecting the graph on the y-axis. And this is because you're basically changing. So if we had a y equals x cubed graph, this would be much more obvious, but this is y equals x squared. So for example, if you have 1 here, and then you times 1 by negative 1, that would become negative 1. Negative 1 squared is 1. Let's say 2. 2 times negative 2, 2 times negative 1 equals negative 2. Negative 2 squared equals 4. And that's why this part is 4. But this is just, it's a bad example in terms of reflection. But all you need to know is that when you times x by minus 1 before putting it into the equation, you are reflecting the graph in the y-axis. Now stretching. If you times the function by a scale factor, then the whole graph is stretched in the y direction for that scale factor. And this is because, again, you're changing the final value of the function. Let's say, again, that x equals 2. When you square that with y equals x squared, you get 4. And then you times to the final answer, you get 8. Every corresponding y value is getting times by 2. And so the gradient is steeper. And so this graph is stretched upwards. Meanwhile, and it's quite counterintuitive with x. But when you change x by a scale factor, so in this case, I'm showing an example of you're timesing x by 1/2. You're dividing x by 2. The graph is actually stretched in the x direction by a scale factor of 2, the inverse of 1/2. And that's because basically every value of x is becoming half of itself. So let's say we have 2 again. However, you times 2 by 1/2, giving you only 1. And 1 squared is only 1. What about 4? You times 4 by 1/2, you get 2. 2 squared is 4, while 4 squared is 16. And you can see how this it causes the x value to be almost, I would imagine, as being diluted. But if you think about it logically, this makes a lot of sense. So, and just remember, the changes to x values are very counterintuitive. So if you divide x by 2 before putting it into the function, you're actually stretching the graph of y equals fx by 2 in the x direction. So let's do a little bit of practice with this idea. So here we have a cubic graph y equals fx, and we have the axes and values, and we're going to transform it. So starting with this, we're adding 2 to the function. This would simply move the function upwards by 2. And so we'll move all the important coordinates up by 2. So the y-intercept will move to 0, 4. The x-intercepts will move all up to like their x value and then 2. So this would move up to -1, 2. This would move up to 2, 2, and 4, 2. The turning point here as well would also move up by 2. And so you would have this graph. All right, here we're adding 1 to x. And this means that every x value is actually 1 more than it should be in terms of what it gives like as in terms of what y represents. So 1 would represent the function of 2, and -1 would represent 0. So basically we're moving the graph towards the left because it's quite counterintuitive. So we'll just move the graph towards the left, and so the x-intercepts move to these spots, and the y-intercept moves to -1 rather than x equals -1, and the turning point is at 2. Here, we're timesing the whole function by 2. And so we're stretching all the y values corresponding to every x value by 2. We're increasing them by a scale factor of 2. So the y-intercept that was at 2 is now at 4 because we times the y value by 2. The x-intercepts are still the same since their y equals 0, and 0 times 2 is still 0. Most importantly, the turning point at the bottom, which used to be at 3 minus 1, we times 2 to that y value, and it becomes 3 minus 2. And this will be our graph. Notice how it's like stretched. Oh. Okay. Meanwhile here, we're timesing x by 2 before putting it into the function. This means that every x value is representing double its value. And so the graph is actually getting stretched. I'm actually getting stretched with a scale factor of of 1 over 2. So it's actually getting squished in the x direction. Because 1 represents 2, 2 represents 4, 3 represents 6. So the y-intercept would still be the same because here the x value is 0. Meanwhile, the x-intercepts are moving towards the origin since, for example, 2 is represented by 1 now, and 4 is represented by 2. So, and 3 will be at 1/2. So the x-intercepts would be 1, 0, 3, 0, and the turning point would be at, no, not 3, 0, at 2, 0, and the turning point will be at 1.5 to -1. And also, the x-intercept on the negative side of x would be -1/2, since it was 1 before. And as you can see, the graph is stretched considerably. Okay. Now we're going to times the whole of the function by -1. This basically flips the function on its y-axis, and so every value will be reversed for y. The x-intercepts will stay the same since the x-intercepts y is 0. The y-intercept will be flipped over from 2 to -2. And the turning point that used to be at -1, at 3 minus 1, will now be at 3, 1. And the graph will look like this. Okay, I did really bad there. Now, we're timesing the x by -1 before putting it into the function. Here, we flip the graph on the y-axis. So, the x-intercepts that used to be at 4 and 2 now move to -4 and -2. The turning point that used to be at 3 minus 1 are now at -3 minus 1. The y-intercept stays the same, and the other x-intercept is here. And so the graph will look like this. Okay. So these are all the principles of transforming graphs. Now we move on to odd and even graphs. The definition of even functions is that when you substitute, when you times x by -1 before putting it into the function will still remain fx. This is exemplified by the y equals x squared graph, where if you put the x value, like for example, if you substitute minus x into this equation, you'll just end up with y equals x squared. The function is unchanged. Meanwhile, odd functions are when if you put minus x into the function, you'll end up with the function times by -1 minus fx. This is exemplified by the graph of y equals x cubed, where if you substitute minus x into the equation, you will end up with a minus of the function. And we're going to do some questions on this as practice, but make sure just to remember these simple definitions. Sorry for the cut, guys. If we figure out whether this is an odd or even function, we have to substitute -x into the equation. Here we expand it to be -1 over x, and this is also equivalent to -fx. And since when we put -x into the function, it results in -fx, we know that the equation is an odd function. Okay. We do the same here. We substitute -x into the equation. And we expand it. This gives us x to the power 4 and plus x to the power 2. And this is simply gx. And so, therefore, we know that this is an even function, since it remains, after putting -x into the equation, it is still gx. Finally, with this one, we expand this equation to be x squared plus 2x plus 3. Here we see that the equation itself is not the negative version of the equation, and it's also not the same as the original equation. Therefore, we know that this is neither odd or even. There you go. This is how you do really simple even and odd functions, and how you transform graphs. Thanks for watching.